Okay, our last talk will be multi-view domain-adapted sentence embedding for low-resource unsupervised duplicate question detection, presented by Nina.
Yes. Hi, everybody. Thanks for sticking around for my talk. I know it's getting late. So my name is Nina, and I will be presenting our paper on multi-view domain-adapted sentence embeddings for low-resource unsupervised duplicate question detection. This is joint work with my supervisor, Hinrich Schütze. I will start this talk by giving a problem statement. Then I will present our method, present experiments on 2 data sets, and that'll be followed by a conclusion. So the task of duplicate question detection has already been defined by my colleague Andreas down here. So we assume that we have a set of known questions S and a new incoming question Q, and we want to find all members of S that Q is a duplicate of. And by duplicate, we normally mean something like being semantically equivalent or almost equivalent. And there is a relaxed version of this task, which is what most shared tasks and data sets are actually based on, where instead of classifying S, we simply have to rank it by the probability of Q being a duplicate. To give you a more motivational example, this is a screenshot from Stack Exchange Windows Phone. Here, a relatively new user asks a question about adding new alert tones to their Windows Phone 8. And a more experienced user down here points out that this question is actually a duplicate of a previous question, and that answers to the new user's question can be found in that thread. Now, if you look at the dates, you will see that the question was asked in June, but the link to the duplicate wasn't provided until November. So we can safely assume that this user's information needs weren't met in a timely manner because it took 4 months. And this is where automated duplicate question detection comes into play. Now, the task of duplicate question detection is usually addressed as a supervised classification problem, where we take existing labeled duplicate question pairs, such as the one on the previous slide, as positive examples of duplicates, and randomly draw question pairs from our corpus as negative examples. And we train a supervised classifier to keep these 2 groups apart. But if you actually look on Stack Exchange, you will find that we lack the data to do so in many forums. On Stack Exchange, half of the forums have 160 duplicates or less, and you can imagine that training a classifier on that little data might be challenging. So what are our options in these cases? One option, which has been addressed before, is to train on a high-resource forum with some sort of domain adaptation, such as domain adversarial training, in order to make the classifier transferable to the low-resource domain. Another option is data augmentation or weak supervision, and we've just seen that 2 talks ago. And a third option is to do unsupervised question similarity using representation learning. Now, Andreas said that this doesn't work, and I'm about to prove that that's not the case. So for unsupervised question similarity, we assume that we have an unsupervised sentence encoder F, and that we can use the similarity of the encoded questions Q and S as a ranking score. And here we're using cosine similarity, but there is no reason why we might not also be considering other similarity metrics. So the big question is, where do we get F from? We tried a few encoders from the recent literature, and none of them were giving us good results. So we sat down and thought about the qualities that we would want F to have. For example, we want F to be domain-specific, because we assume that the similarity of 2 questions is going to depend on certain very domain-specific words. But at the same time, F should be high coverage. It shouldn't be surprised when it sees a word that hasn't been uttered in that particular domain, that particular forum before. F should capture lexical semantics and similarities, but it should also be able to deal with syntactic and contextual phenomena, such as figuring out which word is the topic of a question, telling apart questions and auxiliary statements, and so on. And that's a lot to ask from a single sentence encoder. So instead of using an existing sentence encoder or training our own, we decided to go back to the literature, find some sentence encoders that each tick a few of these boxes and ensemble them using unlabeled in-domain data only. And the ensembling strategy that I'm about to present then gives us something that we call Embeddings, namely multi-view domain-adapted sentence embeddings. Okay, so how does this work in detail? In the following, we use a generic notation for sentence encoders, F1 through Fj, where every Fj maps from the infinite set of possible sentences to a fixed size vector. Now, our intuition is that there exist groups of features or directions in the output spaces of F1 through Fj that, quote-unquote, mean similar things in the domain. And if we're able to find these directions and map them together in a new shared space, that should give us embeddings that are semantically richer than the embeddings we would get by simply concatenating or averaging encoders. And the method that we use to find and map these groups of features is called canonical correlation analysis. Full disclosure, I'm not the first to do this. CCA has previously been applied to ensembles of word embeddings, most notably by Rastogi et al. In 2015. So one way you could think of our work is that we are taking their methodology from the word level to the sentence level. So let's briefly review canonical correlation analysis, or CCA. In CCA, we assume that we have two random vectors, x1 and x2, and we're looking for two vectors, theta1 and theta2, that maximize this correlation term. And usually we will repeat this process iteratively, such that the projection that we get at iteration k is uncorrelated from all previous projections. We don't show, Buck and Jordan show, that this can be rewritten as a generalized eigenvalue problem like this. So on the left, you have a block matrix that contains the cross-correlation matrices of x1 and x2. On the right, you have their, not correlation matrices, covariance matrices. And on the right, you have their within-view covariance matrices. And the thetas that solve this equation are the thetas that we're looking for. Of course, we're not interested in two views, but because typically we'll be considering more than two sentence encoders. So we need a way to generalize this to 3 or more random variables. And Buck and Jordan do this by simply extending the generalized eigenvalue problem. Now, this isn't the only way to do this, but this is the way we went with. Again, you have cross-covariance matrices on the left, covariance matrices on the right, and we're looking for theta. And also note that typically we would add a small positive term to the diagonal of the matrix on the right to make the whole thing more stable. So how do we apply this to our situation? Recall that we said in the beginning that we would train on unlabeled in-domain training data. So that's a sample from the infinite set of possible sentences. And in our case, this will be the set of all unlabeled questions from the forum that we're interested in. When we apply the encoders to S, we can estimate mean vectors, like so, and covariance matrices and cross-covariance matrices, like so. And when a new query Q comes along, we feed it into the individual sentence encoders, center it, project it with the thetas that we found by solving the eigenvalue problem, and that is our final sentence encoding or embedding for question Q. Now, before we move on to the experiments, I briefly want to say what it is that we actually put in the ensemble. So in our paper, we settled on 4 sentence encoders. 2 of them are generic, and 2 are domain-specific. 2 are contextualized, and 2 are simple averaged word vectors. So in the top left corner, you have glove vectors. These are downloaded from Stanford NLP. On the top right, you have fast text, and fast text we trained on the unlabeled questions from our forum. In the bottom left, you have the universal sentence encoder by Daniel Chair. We use this as an off-the-shelf model. And on the bottom right, you have BERT. Now, in the case of BERT, we downloaded the pre-trained model, but continued training it as an unsupervised language model on the forum data. And then at test time, we simply average over vectors. What's important to note here is that Embeddings treats these encoders as black boxes, so you could easily add new encoders, replace them. You could even put a web service in there or something that you don't really have access to. Now on to the experiments. So for this, we work on, or our main results are on stack exchange data, and our corpus contains 24 forums. Now the first 12 forums come from the CQA dubstack corpus, and this corpus was actually meant for supervised training, so it's reasonably high resource. So therefore, we supplemented with 12 really low resource forums, and by low resource we mean having between 100 and 200 duplicates, labeled duplicates that is. And you see that the number of questions per forum is somewhere between 3,000 and 10,000 in each case. And we also keep 4 forums as held out data for certain design choices, and the rest of the data is our test data. And also you can find the low resource forums at this URL. Speaking of design choices, we wanted to make sure that fitting GCCA on the in-domain data is actually a good idea. So what we did here is we used data from the billion word corpus instead. This is mostly news data. And you see that even though this corpus is a lot bigger than our domains, the performance on the in-domain data is better. We also checked if continuing to train BERT as a language model on the domain is helpful. Again, we found that it is. And there's more ablation studies in the paper. Now on to our main results. Our first baseline is BM25 as implemented in Elasticsearch. And for our second baseline, we used the domain adversarial LSTM from Shah et al. At EMNLP last year on the low resource forum. Now, this is a supervised domain adversarial setup, so we need one source domain for every target domain. What we did here is we tried to heuristically allocate one CQA dubstack forum to every low resource forum. However, for many forums, this didn't actually work because there was no good source forum. These are our individual encoders. And you can see here that with the exception of the universal sentence encoder, none of these are really competitive with BM25. This is what happens when we simply concatenate the output of the encoders. Things are looking a lot better here. This is MV days. And then finally, this part is not in the paper. We also tried adding the sentence BERT model to the ensemble. Now, sentence BERT is going to be presented at a poster session tomorrow, I think, and it's another generic sentence encoder similar to the universal sentence encoder. And we got some more gains from this. Now, we also tried MV days on the 2017 semi-val duplicate question detection shared task. This is the information retrieval baseline and a bunch of results from related work. These are the individual encoders. Again, the universal sentence encoder is the only one that's kind of competitive here. This is concatenation, and this is our result. And as far as we know, this is the current state of the art. And note also that there are some supervised models in the related work. So this is actually a supervised task, and what we did is we just threw away the training labels. So to conclude, I have presented MV days, which stands for Multi-View Domain Adapted Sentence Embeddings, and it's an ensembling method for sentence encoders on domain-specific data. MV days is unsupervised. It's flexible, so it's easy to extend to new sentence encoders. We have shown an evaluation on high and low resource community question answering forums. And what we're trying to figure out right now is whether this method has potential for other unsupervised sentence level tasks, such as semantic textual similarity, sentence clustering, etc. Thanks for your attention, and I'm looking forward to any questions.
Thanks, our speaker. So, any questions? Any questions? We have plenty of time for. Okay.
Hey.
Hi.
So one can imagine that, let's say you've got a bunch of encoders. You want to be able to ideally tell that each encoder is contributing to sort of the overall performance of the ensemble.
Yes.
Do you think your method can allow you to, for example, figure out that you don't really need the glove embedding because you already might be capturing some of that information?
So we have some Bayesian studies in that direction in the paper. It actually turns out that the glove embeddings are useless on the high resource forms and the fast text ones are useless on the low resource forms. So we ended up using them both. Okay. But in the method itself, I'm not sure if we can look at the projection matrix and figure out that okay. There's, yeah.
Okay, any other questions? I actually have a quick question. So in
Sure.
your results tables, one of the tables, there's no results for high resource question. Yeah, this one.
Yes.
And yeah.
So that's because in the ADA setup, which is by Shah et al., you assume that you have a source domain and a target domain, but you evaluate on the target domain. What we did here is we used the high resource forms as source domains and the low resource forms as target domains, so we only evaluate on the target domains. I guess we could have found even bigger forums to use as source domains for the high resource ones, but we didn't do that.
Yeah, that would make more sense. I mean,
yes.
Yeah. Okay. If there are no questions, so we will happy to end this session. And let's thank our speaker again. Thank you for coming.